Okay.
Please.
Okay, so I will tell you about quantum simulation string breaking dynamics, but let me first start by maybe stating some obvious things, which I think we probably all agree on. So we want to find a problem that quantum simulators can solve efficiently, that classical methods struggle with, yes, and addresses interesting physics. Now, okay, there are many ideas, many different directions one can take. Personally, I think studying time evolution of many body systems is probably where we should take, and this is quite a widespread opinion because we know that this is what quantum simulators are best at, and it's typically difficult to do time evolution with classical methods. You usually find problems there. And there are many interesting physical questions that have to do with the non-equilibrium dynamics. So, and to show a few, I'm taking this nice picture from these review papers like Christian Zoller and Martin. And here, okay, this is teamwork. This illustration, you see a few examples of problems that are also non-equilibrium problems, like, for example, the dynamics in the scarce-yearly universe, so neutron star core, and problems about energy transport there, and also high-energy particle collisions. And in particular, how do you model, like how do you understand from initial methods the process of hadronization and fragmentation there. And in particular, in this last question, I think that the intuition is that to understand this, we just start from a simple, the simplest case that we can think of, that's the one of string breaking. So the idea here is that, okay, for those who, like me, do not come from chromodynamics and we are not familiar with what string breaking is, I think the idea is actually very, very simple. If you have, like, say, quark and antiquark that are bound together by string, so this is like a gluon, that bind them together, and if you imagine like increasing the distance between them, pulling them apart, well, the energy of this string is growing linearly with the distance, so at some point the energy is too large and it's more favorable to just break the string and produce two more particles, okay? So this is the general idea, the intuition, why this happens and why you cannot just isolate a single quark, right? And you can also see this, and the way how this is usually studied is by looking at the potential between these particles as a function of their distance. So there is this linear part here where, okay, this is what I explained earlier, that the energy of the string is growing linearly with the distance, but at some point, instead of growing indefinitely, you see this saturation, and this is because you essentially hit the threshold for producing two particles, so this is the particle mass. Okay, so this is the general picture. This is like what you expect to see at equilibrium, so in essentially the ground state. So this is what, if you think of what are the state of lowest energy as a function of R, but you can also imagine asking a similar question dynamically, and probably this is what is more interesting to describe what happens after a collision. So for example, you could ask, what if you increase this distance over time? Is this what you would see? Like, would you see this kind of breaking? Maybe, okay, this is what we would like to do, but we all know that it's too difficult to study this in QCD, and so there were many attempts recently trying to study this in simpler theories. We want theory where you have confinement and that can be experimentally realizable. And there have been many different works in this direction. So these are all works that study string breaking dynamics in different theories and different experimental setups. So these are all works that were like run on some quantum hardware. So let me go through them one by one. So this one was Z2 lattice gauge theory in 2+1 dimension. This work was done by the Google team, superconducting qubits. This was this work studying a U1 lattice gauge theory in 2+1D. This was the Gridberg atom arrays, Guerra team. There was this work on Z2 lattice gauge theory in 1+1D. This is the one I was involved in, and this was done, so the experiment was done at Duke in the trapped ion group. And this one is a C2 lattice gauge theory in 1+1D. This was done by Anthony here in the audience, who ran these simulations on an IBM machine. And finally, there was this other work that studied U1 lattice gauge theory in 1+1D, and this was done with atoms in optical lattices. So I don't know if you know this, but okay, there's many different theories, different experimental setups. All these papers came out essentially within 2 months from each other. If you just look at this code, you realize that essentially all these different groups worked on the problem of string breaking at the same time. So maybe rather than going in the details of what we did, I think maybe it could be more interesting for you to hear about what is similar and different, about the similarities and the differences between these different approaches, right? Since all these works were essentially done in parallel. So, okay, so I will not explain how all these different models were implemented. I will just try and tell you what kind of phenomena were studied and tell you about the results of these works and compare them. So, for example, one thing that some of these works studied was studying essentially ground state properties by preparing the ground state with some quasi-adiabatic ramp. So this, for example, what we did in our work, so you can imagine this is essentially a phase diagram. So these are some parameters in the model, and the blue region is where the ground state is a string, the red region is where it's a broken string. So for example, okay, here on this line, this is a classical model. We know exactly how to prepare these states, and so we can just run these ramps, like we can quasi-adiabatically prepare the ground state here, and also the first excited state. So what we can reconstruct, for example, at this value of the transverse field is the energy dependence on this parameter. So we can essentially see this crossing between the string state and the broken string state here. So this was done by preparing this ground state and measuring the energies. A similar thing was done in this other work, where so this was the predicted phase diagram, and they also did some quasi-adiabatic ramp to prepare these ground states, and they were able to essentially essentially measure this separation line between these two phases. That's this line here. And something similar was also done in this work, where they prepared this ground state and found regions where you can have a string or a broken string state. Okay, so here I would say this was very similar done in its different works. Another thing that was studied is the quench dynamics. So this is like work by Anthony here, and okay, so this is time, this is space. So this string was prepared in this initial state, and there was essentially two main features here. One was this oscillation, and the other one was this. You can see very clearly, but essentially, this here, which represents some maybe with this point. Okay. So these here are essentially are there because the string is breaking, and so you can have essentially the lighter particles flying away. and so this was the numerical simulation, and I mean the experimental data. Okay, it's hard to access long enough time to actually see this signal, but still the oscillations were there. And yeah.
What's the observable here?
Right, so here probably, so we can
Yeah, so you
explain.
can think of the observable as being like a pore density. So, or just like showing the charge distribution.
But in physical devices, it's like local
It's easy.
It's easy. Cool.
Yeah.
So,
Yeah.
is there something like a string wave packet? So when you have particles, you can create wave packets by using the
Right.
degeneracy and then Fourier
Yeah.
analysis. But for string, you have, so in a
Right.
even generator, what counts is how much energy you have in the initial system. So if you have quark anti-quark pair with a lot of energy, then they produce a lot of particles. And so there's a logarithmic scaling that we should try to achieve in these things. But I cannot get my mind around getting the two ends of the string to be individual wave packets. So it's big,
Yeah.
so I don't know if you have any idea.
Yeah,
So
indeed. This is also one difference between different works, I think. So, for example, in what we did here, this we prepared a string with like static charges. So these
Yeah, that's what it is.
don't move.
Yeah.
so in that case, we cannot do that.
Yeah.
I think in these other cases were dynamical charges, correct me if I'm wrong, but still they didn't have any momentum imprinted in them, so they were created locally, but localized there. But I think that's what we should hopefully try, and in the direction we should try and
Yeah,
take
maybe
to maybe
different
have.
length with different momentum to make one move to the left and the other to the right.
Yeah. I think in principle you can imagine doing this. It's of course has some more complication, I guess, to the initial state preparation.
So you talking about the initial charges to build the configuration around having them move.
Yeah.
So those have been done in one, classically, by the group Stony Brook.
For instance, we can make a wave packet with three locations for particles, so we would have 3 and 3 on each side of the string. So if we can have string with a size 5 or 6, we could have two wave packets moving in opposite directions.
So we did classically, and I don't know if you've heard, is to have static charges and then find the ground state configuration measures and move them across the lattice, and that's what happens. But that was a classical, it's not that.
Yeah, so I think there's also other works, other groups did something like this, preparing like in a classical, say for tensor networks, is something you can do to prepare these wave packets in your initial state and evolve them. It's like it's of course, if you want to do it on a quantum system, like you need to know how to prepare the wave packets. But in principle, I think you can.
It's unknown how to prepare them, or is it just because it can't be done efficiently enough given the limitations of the devices today?
I think it's because it's hard to do this efficiently. I mean, there are proposals or ideas for doing it.
I mean, it's been done in one.
In
It hasn't
some
been done in
models.
two.
I mean, if you think in terms of electric field and the charge and radiance, the charge should be more, even the gauge degrees of freedom are in between, so it's a little difficult. I think it's possible. It's more complicated for single parts.
But it's true, it has been done, so. Okay. Yeah, so as I was saying, we do something a lot easier. We just have static charges, so they are really pinned in one position. We only study the dynamics of the region, like the internal part of the string, basically. That's the only part we simulate. And we observe something similar to these oscillations, like here, for some reason I don't want to go into, they are up and near the boundaries, but essentially, okay, we can see how this the string, like how this evolves in time, and we have some understanding for what we observe here. And something interesting you can find when you do this kind of quench experiments is you can find resonances that correspond to essentially some special conditions, like so this sigma is the string tension, and this r is some distance. So this is the energy, sigma r is the energy that you gain by breaking the string, like this, and 2m is the energy you need for producing these additional particles, right? So if you meet one of these conditions, basically this kind of process is resonant, and you will see these oscillations in the dynamics. And this is something that I think many people have studied. For example, what we did here is the following. So we know that here, at this point, for example, we know that these two states have the same energy, right? This is the transition point between the string and string breaking. And so if we do a quench, say from this point to these different points here, we observe some oscillations, and the amplitude is largest when the string tension or this longitudinal field is basically here. So here I'm plotting the amplitude of the oscillations as a function of this parameter here, and there is a peak if you are close to this point where the energy is. So this we did essentially for this system sizes. So this corresponds to a resonance of 5 spins flipping together, essentially. Similar things were done also in other works. For example, here, so they started with this string configuration, and this was in 2D, so in this honeycomb lattice, and they looked at all these different patterns for breaking of the string and found the values of the parameters where some of these have the same energy as the string, and they found that in correspondence to these crossing points, they had some peaks in a similar kind of experiment. So this was the one with Rydberg atom arrays. Something similar was done in this work by Google. They essentially had this this resonant process where you break the string here, and you have these red blobs represent the charges, and the string is broken here. And so, as a function of these parameters, there is a peak corresponding to the value of the resonance. Okay, so this is one thing that you can study in a quench, and I think it's very similar if you do it in 1D or in 2D. Essentially, it's just a matter of energy, matching the energies of the two states. Something interesting you can do in 2+1D is that you can have non-trivial string dynamics. So in 1D, for example, in our case where we pin the position of the charges, so if the string doesn't break, there's not much you can do, right? It's trivial. But in 2D, something you could study, for example, is the vibration of the string. So this is something that in this work, they prepare it for example, like this, and they observe these oscillations to the other side. And also in this other work, they essentially studied how, say, in different parts of this phase diagram, how this different configuration of the string, like what were the weights, the relative weights between these different configurations.
Could you in principle consider multiple strings?
What?
Could you in principle consider multiple strings?
Multiple strings, like...
Like essentially, for example, there you can go the other way, for instance. Or by symmetry, they are completely equivalent.
No,
Because
so,
you talk about vibration, but
Yes.
that means that you have more than one at the same time potential.
yeah, you have this additional degree of freedom
Yes,
that
of course,
corresponds
yes.
to this transverse mode. So, and it's true that like all these different configurations correspond to different energies classically. So you see something different if you prepare your state in one of these configurations, and yeah.
Okay, I see. Yes, okay, fine.
So maybe a question along the lines, and I think I may have asked some people in the discussions already. I mean, all of this is sort of meson physics, right? So did people also look at baryonic type of spins where they split up and this sort of?
Not that I can think of in quantum simulators, at least. Probably classically, I'm not sure about it.
More generally, I mean, does this happen in Z3 already? Or do we need something more complicated?
Yes.
That you can have like, I mean, in Z3 you should be able to have 3 spins meet at a vertex, right? So I think in Z3 you can get a baryon, but should be
I
possible,
think
right?
so. I think so. Yeah. I don't know. I don't think I've ever seen anything like this in, but
Again,
it's
the
possible.
group at Stony Brook today will look at things like this, looking at what are the actual flux tube configurations in a baryon. They haven't put anything on machines yet. So
I remember there was a talk by Rob Bizarski at some point
on
where he-
Z3.
on
Yeah.
Z3, but I thought it was on 1D, but I'm not sure.
Yeah, it was just the first discussions of Z3, so they
I
haven't
see.
done full scope dynamics yet, or anything we're actually talking about, but they're preliminary moves in that direction.
I
If
see.
you have SU2, then you have a two quarter variant, so that you can get them in Z2.
Sure.
So a general question. So this Google calculation are very expensive because they have to make this plaquette interaction, and I looking at the diagram, it gives a headache. People who do event generator, they go in the center of mass of the QQbar pair, and then they use a 1+1 dimensional model, which is very cheap compared to the 2+1, and they treat the transverse degrees of freedom perturbatively. So I wonder if this question that we have to ask, is it better to do a 2+1 full-fledged or doing a 1+1 with intelligent correction?
I think the comparison between the two will answer your question.
Why we pay him the big money?
We should.
I think that's one of the early outcomes, right, is to understand if there's differences, exactly those types of differences.
Yeah. No, I agree. I think it's like the fact that there's all these different setups, different models that have been studied. I think maybe this is something that we could try and think of. Like, okay, if we understand what happens in 2D, like, do we get the same result if we do this in 1D? Right? Maybe this is something that this could be useful for.
The initial state has a lot of momentum in 1+1. So that's, if you prepare this, then maybe you can have a symmetric treatment.
So maybe this is not necessarily that important. Yeah. Okay, so let me summarize a little bit what I've talked about so far. So there were different models. So somewhere in 1+1 dimension, there is G2, the trapped ions, SU2, so conducting qubits, 1, optical lattices, 2+1, so G2 and V1, and a different phenomenology as well. So studying the ground state, quench dynamics and the like resonance string breaking in quench dynamics. These dynamics of strings in 2+1D. And now we'll focus a little bit more on this ramp dynamics for the that I haven't yet talked about, but let's see how much time I have. Not much, but okay. So it's okay. I've shown you this picture before, right? This is like a static potential, how we understand string breaking there, and I also said, okay, what if we try and study these things dynamically and we change this distance as a function of time? So this is what we wanted to do. Actually, this seemed yet a bit too difficult, so we did something simpler. So instead of increasing the distance, we increased the string tension as a function of time. So this h here is the string tension, and what this represents is like, okay, this string that becomes stiffer and stiffer is how we can think of this problem, and if you increase the string tension after some threshold, then you also have string breaking. So, and this is easier because, okay, we're on a lattice, we just keep our particles there, and we can tune these parameters as a function of time. So this is something we can do. We can change this in time. The way we model this, so I mentioned earlier this Z2 lattice gauge theory, which is equivalent essentially to a Z2 to an Ising model. So this term here represents the energy of a domain wall, so the mass of these particles, so all particles are domain walls in the Ising model, and the string is represented by these down spins. So this longitudinal field essentially gives some energy to the domains that point in the down direction. Okay, so and this is the transverse field that allows.
So your J are long range?
So yeah, that's a great question. So in this experimental setup with trapped ions, what we have are exponentially decaying Jij.
They can go across the wall.
Yeah. So we have basically some tails here coming from the interaction from the external spins. Yes. So, okay, so this is what we do. So, as I've said, we change the string tension as a function of time. So the lower energy spectrum as a function of the string tension looks like this. There is this like level crossing, well, an avoided level crossing. So if we increase the string tension, the ground state goes from being a string to being this broken string. So this is what we do in practice. We start from all spins pointing down. We turn on the transverse field. This we do slowly, so adiabatically basically, so that we prepare this ground state here. And then we turn on this longitudinal field, so we go across this point as a function of time, and we do it by evolving for some time tau. So what should happen here? Well, we know essentially from this simple picture of a two-level system. This is basically a Landau-Zener physics. So if tau is long, so we are essentially adiabatic, then so this is the probability of ending up in this excited state. So if tau is long, there's very low probability we are basically adiabatic. So we're here. But if tau is small, so we go very fast, we stay in the string state, and so this P probability of being in the excited state is large. Okay, so it's, so we did this, and we looked at this in the trapped ion experiment. So this is what the probability of being in the, say, ground state and first excited state looks like as a function of the total duration of this ramp. And so first of all, one thing, so how do we measure these probabilities? So what we do is once we ramp this longitudinal field, then we turn off the transverse field so that we can map these two states back to the all up and all down state, and then we just measure the probability of finding that P string. So here we have So this is the probability of having all the 5 spins down, all the 5 spins up, and you see as a function of the ramp time, basically, is what I told you before. So if you go very fast, you stay in the string state, but if you go very slow, you are mostly in the broken string state. So this works essentially because we only have a string of size 5. And if we try and do this for longer strings, we will never see all the spins flipping together, right? This is very hard because we need to flip L of them. At the same time, this gap is exponentially small in L. And so we can never be adiabatic, essentially. So because the gap is too small and the evolution is diabatic, okay, so how does the string break in this case? So the idea here is that, well, there are other states that you cross, right? There's not just this state where you have to essentially produce this particle and have them tunnel a long distance. You also have states where you produce their particles and they tunnel through a much shorter distance, essentially. And so this is something that we probe for larger systems, like 13 spins. This is like the value of magnetization, so these are all spins pointing down as a function of time. This is the duration of the ramp. And now if we increase this tau, we start to see this breaking. So and the idea is that the slower the ramp, the smaller the value of h where we see this breaking, and also we form larger bubbles which represent essentially regions where the string is broken. So the slower we go, the more this can essentially happen. We also see something I think is very interesting, like if we plot the average magnetization as a function of time, we have some scaling law that. So I think in similar words, this is being called a generalized Kibble-Zurek. This is not a Kibble-Zurek because this is not a continuous phase transition that we're crossing. It's more similar to a discontinuous or first order phase transition. So I think it's not completely understood, but okay, I think it's very interesting, and we have some maybe partial understanding.
So, can I ask you a question about this configuration?
Yeah.
I missed something. So here I have 2 charges that are fixed distance apart.
Yes.
There's a string, and I'm changing the string constant at some rate.
Yes.
So is there any way I can think about, is there a mapping between that picture and having them move apart at different velocities?
So not exactly, because what happens is, like, if you increase the string tension, then at some point you can also break the string, essentially on short distance, right?
Right.
Well, if you increase the distance, like the condition of string breaking doesn't change. You still have to tunnel a long distance. So here we are manually reducing the distance for the.
There's no rescaling of coordinates that makes these related in some way.
That's a great question. Yeah.
So your charge
Maybe there is.
the walls are closed.
Yes,
Yeah.
yes. Maybe if you carefully rescale, it's not very clear if there's a way to do that. I think intuitively maybe there is.
I just think about what the dimensionless parameters are. Because if you have infinite massive charges, then they're no longer scale.
Mm-hmm.
So I have a distance and I have a coupling.
Right. So these.
That is the blue one.
Yeah. So these are infinitely massive. Then you still have these dynamical ones that you can excite in the string. But
I mean, in principle, in the continuum limit, the relations should be normal, right? I mean, you know the string tension in terms of the coupling, and you know how they depend on the lattice spacing, so
yeah.
it should be possible to bring this with larger field.
I think so, yeah. Because you're also rescaling time, I think, as you
right now as well.
Not sure exactly how you would do it, but I think you could.
Where the distance between the walls increase, I think, and the lattice spacing is increased by including the parameter.
Yeah. Yes, right. So I think
if you reduce the lattice spacing, the number of spacing between the charge should increase to get physical.
yeah, I think physically maybe you're
Because
increasing.
you have a cutoff momentum somewhere
Yeah.
that messes up things.
So that's the lattice spacing.
Yes.
The lattice spacing.
Yes, exactly.
Yeah,
So
if you
that's
get
what I'm saying. I mean,
smaller.
the scaling is not obvious because of that.
So if you increase the correlation length, then your physical lattice spacing.
Oh, but I mean, the statement here is that even in the continuum limit, there's a physics discussion here. It's in
Oh, yeah,
various
yeah,
ways.
that's right. Effective theory.
Right. Yeah. So I think there probably is two things. You can imagine also in the continuum doing something like this, so changing these parameters as a function of time, and you should get something meaningful there, and also understanding, okay, can you think of this as change the distance rather than changing this parameter, and then you have to understand how these different parameters are related and in this continuum limit and scaling there. So yeah. Okay, so I'll summarize this second part. So we studied in this quantum simulation with trapped ions. We studied this kind of Landau-Zener physics as we cross the string breaking point, and what happens for longer strings. So how you have this kind of bubble nucleation phenomenon and these scaling laws that possibly have to do with the fact that we are not that far from the critical point. And I think there's also interesting physics here related to the fact that when you prepare this, when you cross this point, you have this string that is not the ground state and will decay. It can decay in principle, but it just takes a very long time for it to decay. So I think there's very interesting connections with other questions about thermalization times, about metastability, and so on. Maybe a few more questions. I think we also already discussed some of these things before. So, for example, what Henning said about, what about string breaking in particle collision? Like, what you want is probably not what we did so far. You want some dynamical charges that are traveling away from each other with some momentum. So I think there's a question of how, whether anything we did so far and all these different works, are they giving us any insights on some of the physics that we hopefully want to describe in the future? I think
for sure.
Yeah,
I don't know
that's
exactly what it is, but it's almost obvious that it's going to be useful.
right. And how should we hopefully have more insights from there, and how, because we're studying different models and different, I guess it's a question of, is this something that will be useful also to describe this kind of what happens after a collision? I think we should think about it also more seriously now that we have a few of these examples. So okay, I also mentioned thermalization and the fact that you can have someone like me who's interested in non-equilibrium dynamics of many-body system is a very interesting question. Continuum limit is also something we discussed earlier. I think, in particular, this kind of Ising model is a very nice playground because we know how to, we understand very well this scaling limit with Ising field theory. We know how to study these models in a quantum simulators. We have many examples of physical setups that have this Ising critical point, and so we hopefully can make some some progress there. And finally, okay, maybe one of the elephants in the room, also all the things that I showed so far, I'm pretty sure you can simulate on your laptop. And okay, this workshop is also about fault tolerance and you know, going, hopefully we want to eventually do something that goes beyond what can be simulated classically. And okay, and this is all I wanted to say. I just want to thank also my collaborators on this string breaking projects, and it was the theory groups and experimental group. And yeah, thank you for your attention.
Go ahead. Oh, wait, quick question. Are there any interesting additional modes of the string breaking dynamics in 3D system hypothetically? Because in experiments, actually you can generate a 3D quantum system.
Mm-hmm.
So I was wondering whether you expect something interesting.
Yeah, so I think this probably has to do with what I was saying. So in principle, okay, if you have 3D, you will have also more of these additional degrees of freedom. How this will impact the string breaking itself, I'm not sure, but maybe you have some ideas.
Well, so the cost is you have placket interaction. So they have 4 operators, and then you have to play around with and see. So it's very expensive to do, but you have to figure out if it is more than 4 physics.
Maybe something I want to add is that, okay, in 1D, this confinement, you know, is very simple. We understand it classically, right? You don't need to just think of the Ising model. It's very clear why you have confinement there. If you think of 3D, QCD, then you don't have this simple understanding, I guess. And so if you want to understand also why you have this kind of physics there, I think it's probably useful to think of beyond these simple 1D models.
So can I maybe add again my comment about the baryon? Sorry. I mean, sort of now if you're in a 2D plane and you have this meson, you can sort of see vibrations of the string in 2D, right? I'm thinking very naively, if you have a baryon, it can in principle span a plane if you have 3 of them. And I guess in 3D you could see vibrations of that plane. And I'm guessing this would be interesting, question mark.
So people have looked at this a little bit in lattice QCD, right? Sticking down static colors and then asking what are the flux tube arrangements, right? And they tend to line themselves up in a triangular configuration. And so this is sort of what I was mentioning before. People were trying to explore this type of baryon vertex, so to speak. But it's still primitive, and I'd say nothing definitive yet.
But what do you think of 3D quantum simulation of that is interesting? Yeah, okay.
Let me think about that for a minute. Yeah. Absolutely.
No, like, I mean, for instance, Enrique has shown these nice plots, right? That you can see the Lucia term in simulations in 2D.
In 2D, yeah.
And so because basically there's a universal theory of how the string can vibrate as its one energy effective description. And I was wondering sort of what the corresponding theory would be for that object. And I was like, is it like a drum, sort of, low energy, or is it this vertex which
And
does...
the physics is very different. Yes, sorry. So the baryon carries baryon number, and then it radiates spikes, if you want. So it's a very different picture than the meson separate.
You say directly radiates, so there's no...
Yeah, the string is, you don't have the string in an obvious way. So you have a baryon moving, and then it radiates spikes on its way. So it's
But if
No,
you
no,
sort
but
of
he's
make
doing
the
something
masses.
different, right? He's looking at the internal structure. So if I just have three color charges separated, what does the gluonic configurations look like? And that's what I think your question is.
Yeah,
so you can have 2 and 1 and then
Yeah.
have a QQ
So people have just already stepped down 3, right?
Yeah.
And asked what is the color, what is the energy density and the action density, and that is QCD. And you see, really looks like this. Really looks like 3 tubes joining in the middle.
It's a Mercedes-Benz.
Oh,
Yeah, right. So there's good
Okay,
graphics
but
by
Yeah.
Derek Weinweber that just show what this energy
That's right.
density and action density is doing. But and on the quantum simulation side, basically nothing.
but is there a universal low energy theory that is sort of ignorant of the underlying gauge group and so on, but just looks at sort of the fluctuations of this object? Similar to
Typically
the-
not. I mean, there's models and conjectures, like barrier and vertex models and things, but
I see.
QCD is the only way to go.
Okay.
On a different topic, I had a question about your classical simulations. So, how large are these systems that you've been considering? Like, and how large would you like to be able to go? What methods did you use to perform these simulations? Maybe we already said all this earlier.
Yeah, I didn't say much about this indeed. So I can tell you about these works, right? Because this is the one I was involved in. And here we have up to 13 spins. So that's why I said, okay, right, I essentially run this on my laptop and I can do exact evolution there. So in these results here, we didn't really need to make much effort on the classical simulation side.
Just write out the vectors directly.
Yeah, I think so. I'm trying to remember about the other works. I think some of these, probably Anthony can tell about his, but I think some of these had. So this was also quite small, something that we could do. It's exactly there. So in this case, yeah, I think it was, okay, these two works were around 30 and 50 qubits probably. So yeah, the thing is probably in some of these cases, because of the constraints, you can probably understand, like you can actually do the simulation, the dynamics in the constrained subspace and see very similar results.
The dimension of that subspace is small enough that you might be able to enforce it.
I think it's, yeah, for some of these.
Yeah, I'm just wondering, like, I mean, of course, for small systems with like 13 spins, you can of course just write down the entire open space. But for larger systems, like in this 30 to 50 qubit range, like those methods stop working, and you need to start switching to other types of classical simulation methods. And I'm wondering, like, what are the classical simulation methods that would be most effective in that space?
Mm-hmm.
Like would one use like these IQuS simulations, or
Yeah.
you
So
expect that to do well?
I think MPS simulations are the ones that are most, like most of these traces, like, yeah, you would expect
The
to
user state.
like pass. Also,
Fail,
yeah.
ultimately, but
Sometimes a snake, sometimes I think in some of these works we use like cylinders and do simulation on cylinders, or like basically because maybe one of these dimensions is not too large, so you can really simulate this as a 1D system. Yeah, so to my understanding, like what usually for this kind of problems, yeah, we'll compare it with MPS with ignoring the fact that it's 2D, right?
Right, but I guess if you're looking for some of these like oscillatory dynamics, then that is really a 2D question.
Mm-hmm.
And in that situation, you might have to work with a different type of tensor network. Another question is, how worried are you about like finite size effects or edge effects by simulating these systems?
Mm-hmm.
Like, is there a motivation to build a massive spin paths?
Right. Yes. So I would say, so for some of the things we were interested in, it was useful to have a small system. Like these 5 spins, we could actually see them evolving adiabatically and flipping all together. I think if you really want to say something about, and in that case, okay, you just say, okay, I'm studying a small string. Right? But if you want to make statements about the continuum limit, of course, you can just, that's not enough. You can just say, okay, I'll just study the dynamics of 5 spins, you want to have more. And so, I think this is crucial, really, if you want to make statements about the continuum.
I think that's very interesting.
More questions? Is the work that you've done, is it scalable? Like you did a small system of 13 qubits, but can you, in principle, scale that to 50 or 100 qubits in an easy way? Or?
So, okay, so, okay, this was done in the experiment that was done by the people at Duke. So in principle, in their setup, they have, if I remember correctly, around a maximum of 23 ions. We didn't run this simulation on 23 ions just because, like, the more ions you get, the harder it is to control, and the lower fidelities you get. So in like I would say, in practice, it wasn't very easy to scale. Also because in that case, they wanted to really have local addressing of all the individual fields. So one thing that we needed here, for example, to have, say,
If it was a fault tolerant device and it had 1,000 qubits fault tolerant, would you run this model on 1,000 qubits, or would you have to reconsider or read?
Oh no, yeah. Then yes. Then I think. Right, if you have access to more qubits, yes, I think you could run it there, and you can also probably do something more interesting in the sense of what I was saying earlier, like trying and go to the continuum limit in the sense of exploring, the case of, trying to, and essentially here we have, if we have just 5 spins, right, we are really limited by the fact that we have a lattice, but if the more spins you have, the more you can try and push in the direction.
Okay, so we are running late. I think also because I know that there is like a PhD defense in this room at certain point.
12.
Yeah.
So we'll need to get in at 12:45.
Yeah, so quarter to 11 here again.
Sharp.
Needless to say.